Welcome to this lesson on inequalities in one triangle. We start with these first two theorems. Theorem 510 basically says this. If I've got different sides of my triangle, so I know one side's bigger than the other, then I know that the angle opposite the bigger side is bigger than the angle opposite the smaller side. So in this case, what we're saying is that side AB has to be longer than side BC. Well, side AB is opposite angle C, and side BC is opposite angle A. So the angle C opposite the bigger side is bigger than the angle opposite the smaller side. So angle C is going to be a bigger angle than angle A. There. And that's because this side here, AB, is longer than BC. And since angle C is the angle opposite side AB, it's the bigger angle. On the flip side of that, in theorem 511, if I know that the one angle in my triangle is bigger than another angle, then I know the side opposite the bigger angle is going to be larger than the side opposite the smaller angle. So in this case, I'm told that angle Z is larger than angle Y. Well, the side opposite angle Z is side XY. So it has to be bigger than the side opposite angle Y, which is side XZ. So I know that the side XY has to be bigger than side XZ, which is what we've concluded here. In short, bigger side is opposite the bigger angle, smaller side is opposite the smaller angle. And then in the flip, bigger angle opposite bigger side, smaller angle opposite smaller side. Pause this if you need to. Alright, exterior angle inequality kind of goes back to the whole idea of the exterior angle theorem. We know that angle 1 here, being an exterior angle, has to equal the sum of the remote interiors, which in this case are angles A and B. So we know that A and B have to add up to angle 1. Well, if these two angles both have to be more than 0, and they have to add up to angle 1, then both of these angles have to be smaller than angle 1, because combined they equal angle 1. Well, what that means then is that angle 1 is bigger than each of the angles individually. It's the same as the two angles added together, but if I'm just comparing angle 1 to angle A, or I'm just comparing angle 1 to angle B, angle 1 wins. It's the bigger angle. Pause if you need to. Okay, in this theorem, I'm saying that in any triangle, in order to have a triangle, any of the two sides have to add up to more than the third side. And it doesn't matter which side you're picking. Any of the other two sides have to add up to more. So what we see here is a relationship with all three possible setups. So I've picked sides AB and BC, and they've got to be more than side AC when they're added together. I can pick then BC and AC, and it's got to be more than AB. So it doesn't matter which two I pick, they're going to have to add up to more than a third. Now, theoretically, that's what you would do, is you would need to do all three comparisons and make sure that any two add up to more than the third. But when it comes to practically doing these problems, you're just going to look and see, do the two shorter sides add up to more than the longer side? And you'll see how that works shortly. Alright, here I want to write these angles in order from smallest to largest. So the thing I have to identify is which is my biggest side and my shortest side. So I start with the shortest side being GH. It's the one that measures 17.2. I notice that opposite side GH is angle F. So angle F has to be the shortest or smallest angle. Then I want the largest side. Well, I notice that FH is my largest side, measuring 20.4. Well, opposite that is angle G. So angle G has to be my largest angle. So I now know that angle F is my shortest and angle G is my longest, which means H has to be the middle. And as you see, in terms of side lengths, 19.6 is bigger than 17.2, but smaller than 20.4. So it's the middle side, so opposite H is the middle angle. So in order, I'm going to have angle F the smallest, angle H the middle, angle G is the biggest. Now, I want to do the sides in order from shortest to biggest. Now, in this case, I'm missing one of my angles. So I'd want to know what the missing angle was. Angle R here. Well, triangle sum theorem tells me that all three angles have to add up to 180. So I'll just add 72 and 60 together and subtract from 180. I get that angle R is 48 degrees. And now I know that if angle R is 48 degrees, that it is the shortest or the smallest angle in this triangle, which means the side opposite that angle, in this case PQ, is the smallest side. So PQ is the smallest side. But I should also notice that Q, measuring 72, is the biggest angle. So the biggest side is going to be the one opposite the biggest angle, 72, and that's going to be side PR. So PQ is my shortest side, PR is my largest side. Just summing up what I just said. So PQ is the shortest, PR is the longest, QR would be the one in the middle. Pause if you need to. Okay, talking about the rule before that any two sides of a triangle have to add up to more than the third. You can see that happening in the triangle on the left. The two 4s add up to more than the 7. In the one on the right, the two 3s only add up to 6, which is not more than 7. And you see what would happen. These 3s can't come together because they're so far apart. If I bring them all the way down to try to make them touch, there's going to be a gap of 1 unit between the two of them because they can only stretch 6 units between the two of them, but they're 7 units apart. So they're not going to be able to form a triangle. That's why two sides have to be more than the third. And pause if you need to. So the question here is, can these numbers 7, 10, and 19 represent the sides of a triangle? Again, I said a little while ago that theoretically you have to check all three, and I'll show you how that looks. But practically, all I need to know is, do the two smaller ones add up to more than the larger one? Well, the two smaller ones are 7 and 10. They add up to 17. That's not more than 19. Since it's not more than 19, this does not make a triangle. I could, of course, go on and say, do 10 and 19 add up to more than 7? Well, sure. And do 19 and 7 add up to more than 10? Absolutely. But because one of them didn't work, in this case the 7 and the 10, not being greater than 19, I can't have a triangle. It'd have to work for all three of them. So here's another case. I'd want to know if all my methods work. So I'd have to pick any two of them and see if that adds up to more than the third. So again, theoretically, I've got to do this 3 times. Here's what it would look like. So I'm taking any two sides. In this first case, I'm taking the first and second side and seeing, does that add up to more than the third? In this case, it adds up to 5.4, which is more than the third. Then I'm taking the first and the third side. Does that add up to more than the second? Yes, it does. And I'm taking the second and the third side. Does it add up to more than the first? Now, let's talk about why I can pretty much ignore 2 of them. If you look at the one that I've suggested you need, is the 2 smaller ones adding up to more than the larger one. This is the one that really matters. Let's take a look at this second case here, where I'm looking at the first and the third number. 4.6, since my sides are all positive numbers, if I add a positive number to 4.6, in this case 2.3, is it going to be bigger than 3.1? Well, of course it is, because 4.6 is already bigger than 3.1, and now I'm going to add something to it? Yeah, it's going to be bigger. Same thing over here. Is 4.6, if I add a positive number to it, going to be bigger than 2.3? Yeah. So there's no point in checking these two when I actually know the lengths of the sides. This is useless information to me, because one of the sides is going to be bigger than the one I'm checking. That's why the only thing I really need to look at in practical purposes is, do the two smaller sides add up to the third? Do I need to know that any two that I pick add up to more than the third? Yes, that's what's the definition of a triangle. But for checking in terms of calculations, I only need to check this one. Do the two smaller ones add up to more than the third? In this case, they do, so I have a triangle. Here I want to check and see if these three sides could represent a triangle, given n is 4. So I'd actually have to plug in and see what these actually equal, and then I would run that test to see if it's actually a triangle. So plug them in. That's algebra. You guys can handle that. You need to pause this to see how we got these numbers. That's fine. But we have 10, 15, and 12. So what I'm telling you, I'm going to show you all three calculations, but the only thing that really matters is, do 10 and 12 add up to more than 15? Yep, they add up to 22. That's more than 15. It's a triangle. Here's the calculations to prove it. All of them work. The only one that mattered, though, once again, is this one, because I'm looking at the two smaller numbers and saying, are they more than the bigger number? Yep, 22 is bigger than 15. That's what mattered. 15 was already bigger than 12 in this one, so didn't really need to look at that one, and 15 is already bigger than 10 in this one, so I didn't need to look at that one either. Are 8 and 13 and 21 the sides of a triangle? Well, in practical purposes, all I need to know is, does 8 and 13 add up to more than 21? The two smaller ones more than the bigger one. Well, 8 and 13 actually adds up to 21. 21 is not greater than 21, so it can't form a triangle. And you're saying, well, why does it have to be greater? If it's equal, shouldn't it be a triangle? No, because remember the one where we had a length of 7 across and we had the two sides of 3, and we said, well, they'll come down and they would actually have a gap of 1 between them. Here, if I bring the 8 and 13 down, I'm going to bring them down until they touch. Well, where are they going to touch? They're going to have to come all the way down on top of the other line that measures 21. So when they actually finally touch each other, they're going to be on the line. They're not going to form a triangle. It's going to be a line. So they have to be more than the third side so that they meet somewhere above the third side and actually form a triangle. All right. Are these more? Do these add up to three sides that could be a triangle? Well, again, all I really care about are the two smaller sides, 6.2 and 7. When I add them together, are they more than 9? Well, yeah, 13.2, which is more than 9. So, yes, this is a triangle. Technically, you'd need to check all three, but the only one that matters are the two shorter ones more than the longer one. Yes. Pause if you need to. Again, checking some algebraic expressions to see if these are the sides of a triangle. Wondering if that works if t is 4. Using algebra, plug in. Again, you can handle that. Pause if you need to, but our sides are 2, 6, and 17. All I want to know is 2 and 17. Do they add up to more? Excuse me. Try that again. 2 and 16. Do 2 and 16 add up to more than 17? Yep, it's 18. It's more than 17. That's all that matters. The other ones will work. We'll show you all three. The one that mattered is sitting right here. Do the two smaller ones add up to more than the larger one? And they do. Okay. All right, here I'm given two sides of a triangle, and the goal is to find the range of the possible length for the third side. We have to consider three possibilities. One, is my third side the smallest side of the triangle? 2, is my third side the middle side of the triangle? In this case, somewhere between 8 and 13. And 3, is my third side the longest side of the triangle? So you'd actually set up 3 different calculations to check this. Now, this is luckily another one of those theoretical cases where I've got to check all 3 cases. Let me show you what happens when you check all 3. Okay, so here's the case where I'm checking for it to be the smallest side. Okay, so I'm looking, I've got the smallest side, I'm going to add it up to 8 and see if that's greater than 13, the bigger side. And I say, well, I need 5. All right, now here's a case where I'm not sure, and I'm trying to add a number to 13 and see if it's more than 8. Well, I already know that a number, if I add to 13 a true side having to have a length more than 0, that it would be more than 8. So the only way to actually solve this is to get a negative number. Well, we know that sides of triangles can't be negative, so that's pretty much useless information for us, so we'd get rid of that anyway. Then I would try the last case, where I'm saying, hey, I think what I've got are the 2 smallest sides. 8 and 13 are the 2 smallest sides of this triangle. I want to know how big the third side has to be in order for this to be a triangle. Well, what we're saying is that 8 and 13 have to be more than x, so 21 has to be more than x. Okay, so I can't have a third side that's bigger than 21, otherwise these two can't be the shorter sides. So x has to be less than 21, but it has to be greater than 5. Put that together into a compound inequality, and we say that 5 is less than x, which is less than 21. So any number that I pick between greater than 5 and less than 21 would form a triangle. You can try one. Pick 7 as a number. 7 plus 8 is 15. That's more than 13. Pick 12 as a number. 8 plus 12 is 20. That's more than 13. Pick 16 as a number. Well, then that's the bigger side. So 8 plus 13 is 21, which is more than 16. All those things are going to work, and they can form triangles. Now you're thinking, I've got to set up 3 equations. Again, theoretically, yes. Practically, here's what you're checking for. Your range, you're looking for what if it's the smallest and what if it's the biggest. If it's the smallest, then the 8 and the 13 are the bigger numbers. So if I subtract those 2 numbers, I know what my difference is. 13 minus 8 is 5. Look what our lowest number was in our range, 5. Then I consider the case where it's the biggest number. So 8 and 13 are the smaller ones. Well, I'd need to add 8 and 13 together. I'd get 21. 21 was the biggest number in our range. So all you really have to do when you're given 2 sides and you want to know the range for the third side, subtract them and add them. So when I was told 13 and 8, in my mind, I already knew the range because I just went 13 minus 8 is 5, and 13 plus 8 is 21, so it's got to be between 5 and 21. So let's take this one. So again, I don't have to write all this down. I don't have to do 3 equations. I see the 2 sides they gave me. I'm going to subtract them, and I'm going to add them. When I subtract 22 and 17, I get 5. When I add 22 and 17, I get 39. So I'm telling you right now, the range is going to be between 5 and 39. Now I'll show you all 3 equations, inequalities in this case, and show you that I was right by just doing the simple add and subtract method. Here's the setup for all 3. Once again, I have one of the useless ones where I had to get a negative number for a side since that can't happen and actually be a triangle. Look what I had to be. Greater than 5. And x had to be less than 39, reading that from right to left. So compound inequality between 5 and 39, which I was able to get by subtracting these 2 numbers, 22 and 17, and adding the 2 numbers. Pretty simple calculation. So practical purposes here, not a hard problem if I've asked you for the range. Add and subtract, and you're done. Okay, what you need to bring to me tomorrow is this quiz. There's 2 pages to it, 2 slides. So answer these 2 questions. So pause the video. When you're done with this one, move on to the second slide. Answer all the questions. Bring it to class tomorrow. We'll grade it. Have a great day, and thanks for watching. Here's slide 1 of the quiz. And slide 2. I'll see you tomorrow.